So yes, it is started. Hello guys, Navkat this side. So today we will solve this problem, which is GHG and it is power set. And this is a very well-known algorithm, and it has very use cases when you given a problem to generate all subsets, all possible subsequences, or subsequences with a certain condition. So in the given problem also it says that given ABC, and we need to tell all the subsequences where all the subsequences that can be generated using the string ABC. So like ABC, A would be one, AB would be one, ABCS it would be one, BC would be one, and C would be one. These are the subarrays I generated first. A, AB, ABC, B, C, B, BC, and C. But it has subsequences, so AC would be a subsequence. So we have AC also. So I think 1, 2, 3, 4, 5, 6, 7, and 7 is the output. It is not counting any empty subsequence. But if the problem says that all the possible, including the empty one, then it would be 8. So you need to be written plus 1. So like whenever you find a problem to generate all subsets, all possible subsequences where order matter or not matter, so you need to think of a naive solution, and power set in itself is an algorithm that will help you to generate all these subsequences. There can be any interview problem where the question might ask you to deal with subsequences or generating subsets. So one naive solution always would be generate all the subsequences using power set. You can do generate all the subsequences using recursion, that also in 2 raised to the power n. And second thing, you can use power set to generate all the subsequences or all the subsets. So when interview was asking something beyond recursion, then you can say I can do generate all the subsequences using power set. So how this algorithm works, and let me take a very nice example. Here we are given strings ABCD. No, what we do here in power set, instead we don't deal with some certain condition that from I to J, like we do in recursion that I started from I and then look for can I include this particular I, or so if I include this I, the recursion will call go with A. And if I don't ask for the next call, it goes with like this. Here we don't do like that, but the condition or like thing we try to do is we tend to analyze it every number as a bit. Let's say we think that at each index there is a bit associated with it, and for clearance, we just assume for now that there is a bit associated with every index. And if this is 1, that means I'm including this particular D. If it is 0, let's say, so I will not be including this in my subsequence. So like think of a recursion case. There we look for take not take. Here things is being twisted by the way that if the bit is set, that is if it is set, that is 1, we can take that character. If it is not set, we won't take. Rest two are sets, so we can take this, and ABD would be a well-known subsequence or a subset. Here it is given a subsequence. So let me tell you, like if you have to represent the binary representation of 1, this for 2 is this, for 3 is this. So what if I tell you that we can actually use this binary representation? What does actually mean? This means that we can include this first character, but we are not including these two characters. What this means? We can include the character at second index. Assume I'm taking index like this, so I can include this. What this 0, 1, 1 means? This means I can actually take the first character and I can also take the second character. What if I have to take all the 3 characters in ABC, then 1, 1, 1, because I want to take all the 3 characters. So every character index need to be set. So since here we are given the string ABC, and to write the binary, like number of possibilities through which we can actually generate a subsequence of length 3, it would be 2 raised to the power 3 minus 1. That is 2 raised to the power 3, 8 minus 1. 2 raised to the power 3, 8 minus 1. That would give us 7. And what does that mean is I can represent every possibility of having 3 characters using these binary notations. That is from 2 raised to the power 3, because we have n as 3. So, like, don't be confused in a way. Let's just assume that if I have n character, that can be represented in 2 raised to the power 3 minus 1 ways. And if we have n characters, n string length, then we need at least n bits. And to represent each configuration, we actually need 2 raised to the power 3 minus 1 ways. So if n is 3, that means 2 raised to the power 3 minus 1, that would be 7. 8 minus 1, 7. So let's say now I will generate all the possibilities. 0, 0, 0. This is, I have taken nothing. 0, 0, 1. This is the configuration for 1. 0, 1, 0. For 4, 1, 0, 0. 4. For 5, 1, 0, 1. For 6, 1, 1, 0. And for 7, 1, 1, 1. So now, actually, these are all the configurations. I'm taking not I am taking none of the characters. Here I am taking the first one. Here I am taking second one. Here I am taking third one. Here I am taking first and third together. Here I am taking first and second together. And here I'm taking all three. These are nothing but actually the things that I generated here. So if you look this as 0, 0, 0, that means I have not taken any of them. If I look at 0, 0, 1, that means I am including only this C subsequence. Let's say if I'm taking 1, 1, 0, that means these two are set, so I am concerned about AB. So through these binary configurations, we know actually how many strings, how many subsequences we have. So simply, if we have 3 bits, then there are 2 raised to the power 3 minus 1 possibilities, that is 7, and we just generated here. There are 7 ways in which we can actually use one of the configuration, and that binary representation of that number gives us that configuration. And since I started with the fact that if it is 1, we are going to take it, and if it is 0, we are not going to take it. So in this case, we are concerned about like generating all. So since we are concerned about generating all, that means we know 2 raised to the power 3 minus 1 are the possible one. So either like iterating up to n. Why shouldn't we iterate till 7? Because in general, we actually need the binary configurations or binary representation till 7. Because if I iterate till 7, then I can check for this 111 also. Isn't it fine? Because if, let's say, if I only iterate till 3, then I would not be come to a configuration where I'm actually checking with this configuration. But since the possibilities are 3 bits, uh, like 3 bits can be have these number of ways. Like if we have 3 characters, they can be represented in 2 raised to the power n minus 1 ways. Like it is not actually not ways, like those string subsequences can be generated in like in these ways. On like setting one, taking this one, not taking this. Because like if you do recursion also, then also there are 2 raised to the power n ways. So same here, we are trying to generate using power set. So if I iterate till 7, and now what I need to do, now I can iterate for I to n. This is from, let's say, my mask. This is my mask, and mask is from 0 to 7. In this case, we don't need 0 because we don't have empty string, but in general, 0 to 7, and 7 is inclusive. Okay, 7 is inclusive. And now, since like if I am at mask, let's say 1, because we need 1 only, 0, 0, 1. So what I will do, my mask is 1. And now I will check, can I take the particular ith character? And how will I check? So I will check my mask if my mask is set for that character. Currently, I am looking for a mask 001. So here I can only take this index, that is 1, or I will say that that is a 0 index. So I will check is my mask is set for this. From I to n, I can only take 1. And my mask, currently my mask is 1. And if you write it binary configuration, it is 001. So how we actually check? We check if my current, this is I, if my I and, not I, if mask, if mask and 1 left shift by I. Let me make it clear. If mask, we have mask here. If mask and 1 left shift by I. If this is set, what is mask? Mask is 1. And what will 1 left shift by I will give? This is 1 left shift by 0. 1 left shift by 0 is nothing but 1 only. 1 and 1 will give us 1. That means we need to add this particular bit in our subsequence. Since mask is, for this configuration, it is set. I think like for someone who is like dealing with bit masking for the very first time, for them it would be a bit confusing. But like, let me make it very clear. Like I will try my best. Mask is something we know we have 7 possibilities. So mask will go from like 0 to 7. Here we are not dealing with 0 because we don't need any anti-subsequence. So I take 1. So I need to check my mask. Like I somehow using these n length string, I need to make my mask equivalent to that. So when I'm iterating from I to n, I will check is my mask and 1 left by I. 1 left by I means I am shifting my I with 0 bits. So if I have 1 and I want to shift it by 0, actually it would be only 1. So 1 and 1. 1, 0, 0, 1 is 1. So 1 and 1 is 1. That means I can include this particular bit. Let's move for the second character when we would be at I is equals to 1. Yes, when would be at I is equals to 1. So it will do mask, which is mask is 1 at this point, and it will say 1 left should by 1. So it will say move my, like move 1 by, left should by 1. That means left should by 1 means multiplication by 2. So if my 1 is this, now it's saying me do a left should by 1. So it would be 1. So now this gave me 2. Did you get it? Shifting my 1 at bit by left shifting by 1. Now this gives me 0, 1, 0. That is 2. And if I check 1 and, so it will give me 0. And if I like check for 1 and 1 left shift by I, so the 0th bit is not set in my mask because we have 0, 0, 1. And I'm checking that if this particular bit is set in my mask. So it is not set because it is 0. I know it is like it can be complicated. Let's say again, now my mask is 2. So this means it will say me 1 left shift by 2. 1 left shift by 2 means if I have 0, 0, 1 shift by 2 bits, so it would be 1, 0, 0. Like if I set it by 1 bit, shift it by 1 bit, then it multiplied by 2. Earlier we have 1, we will form 2. But now it's saying shift by another 1 bit, like this to 2 bits, so it would be here. So 2 bits we shift, so it would be 1 into 2 into 2 equals to 4, and we know this is a binary representation of 4. So now we will check 0, 0, 1 and 1, 0, 0. I know this syntax might be complicated. Let me boil down this as if if you do 1, 0, it would be 0. It will be 0. It will be 0. That means we get 0. And since we get 0, that means we are not going to include this particular one. And since, so for this subsequence, we have only A. Now we have 2 because we are going from 1 to 7. Now I have 2. So the binary representation will be 0, 1, 0. And I will be checking from I to n the first bit. Shifting like mask is this 0, 1, 0 and 1 left shift by 0. 1 left by 0 is nothing but 1. And if I write the configuration for 1, it would be 0, 0, 1, 0, 1, 0. There and will be 0. That means I cannot add the 0th bit. I cannot add a. Don't look at this example because this configuration comes later. If I do 1 left shift by 1, then it would be 0, 1, 0. And yes, if you do this 0, 0 is 0, but like for this, like we are looking for the second bit is my mask and this bit. So 0, 1, 0. And when you do the AND of this, you will get 0, 1, 0. And at this position, you get 1. So that means we can include this. When we have 0, 1, 0, so we are actually checking 1 left by 1 because we want to check is this particular bit is set. Don't look as a whole. When we are 0, we are looking for is my 0th bit is set. When we have 1, we are looking is our 1th bit is set. When we have 2, we are looking is our 2th bit is set. So here we are concerned about 1 and 1 is 1 is shifted in both sides. That means I can include this and in this way I can form B. I will take one last example. Let's check how this will generate AC. AC would be fine. AC would be fine. This means A, I will be taking this. I'm not including B. I need 101. That means I need 5. So sometimes my mask would be 5 and I will be checking is my mask 1 left by 0. If you do mask is 101, 101 by 001. What will we get? We will get 001 because this bit is set and that means I can actually add A. Next time my mask would be 1. This will give me nothing but 0. Sorry, 010 means 2. And I will check is and of. And if you actually do the and of this, you will get 0. So I cannot include this. Last iteration, it would be 2. 1 left by 2 will be nothing but be 4, 100. And if we do an AND with 101, what we will get? 111. That means this is set and I can include this. So this way, we will also able to add AC. I think I try to explain this. Two things need to be very clear. How we check mask, like how we check the particular, like at that particular index, if that bit is shift, we do 1 left by I. So actually, we are checking is my ith bit is set in my mask 101 I0 if my 0th bit is set in mask. If it is 2, is my 2th bit is set in mask. We are never concerned about getting this whole. We are concerned about is my ith bit is set in mask. If it is set in mask, I would include this in my current subsequence. So for getting all the best possibilities for n is equals to 3, we have 2 raised to the power n minus 1 ways, and that I actually tell you that if you need to form all the subsequences, you need actually 7 configurations and 111. You can actually understand, yes, if there are 4, then you would be needing 16 minus 1, 15. Why? 1, 1, 1, 1. Sometimes this will be 0, sometimes this will be 1, sometimes this will be 1, sometimes this will be 0. So the every every bit has two possibilities. So that's why 2 raised to the power 4, 16 minus 1, 15, because 111 is 15. I think this thing is also clear. If it is 5, 2 raised to the power 5 is 32. So I need to run my mask till 32 because 1, 1, 1, 1, 1, there are actually 32 possibilities. You might find that these are only 5 bits. Yes, these are only 5 bits, but this is the representation of 32. And if I make this 0, then this would be 0, 1, 2, 3, 4, 16, 8 would be 34, no, 24, then 2, 26, 27. This would be 27. So we need to check for every possibility. So some at some time this would be set, sometimes it won't be set. So like if I have to code this problem now, I first need to find the length of the string, that is s dot size, and now we are range. So you can find range either using the power function, it would be 2 raised to the power minus 1, or you can do 1 left shift by n. 1 left shift by n minus 1. What does this does mean? That shift my 1 with n. If n would be 4, if n would be 4, then this this would be 0, 1 shift, 2 shift, 3 shift. Like in this case, if n is equals to 3, so that means, and you have 1, you are saying that shift my 1 by 3. So it would be somewhere it would be here. It would be here somewhere. It would be, you are saying shift my 1 with 3 bits. So 1 would come where 1, 2, 3. So it will be 1, 0, 0, 0, and it will make 8. And okay, I actually said that wrong there. It is 15. But let's say if you have 4, you will say shift 1 by 4 bits. So it would be one shift would be here, second would be here, third would be here, 4 would be here, and this would be 16 minus 1, because we know that we have these much of possibilities, that is 15. So I think you now get this in text. 1 left shift by n means shifting my 1, and this is a bit mask of 1 by nth bit, n bit. So if n is 6 also, then you will say shift it by 6 bits. 1, 2, 3, 4, 5, 6. So it would be somewhere here, and the binary representation would be this minus 1, because we are never need this. We are concerned about these number of bits. Or you can use the simple power function 2 raised to the power n minus 1. So this is now, I already said our mask is from 1 because we are not dealing with empty subsequence. If it has been empty subsequence, I would be checking is this bit is set. Sorry. If this bit is set, if this bit is set, none of these are set. So if I have a string which is empty, it would be empty at the end also, after these iterations also. So I also will get the empty subsequence. So mask is 1. Mask less than is equals to range. If you don't do this minus 1, you can also run till less than range, and plus plus mask. Let's say we have a string current here, and now I have to iterate my string, which is this string the we have given, and I will simply check that syntax if mask and 1 left should by I. If my ith bit is set in my mask, if it is set, then I just need to add this particular character into my answer. Okay, and after this iteration, I can just say result dot pushback current. And since we do not haven't make result yet, let me make a vector of string we need result. And at the end, we can just say return result. And let me compile this. I think they want us to print in sorted order. Okay, so A B A B C. So they want us to print it in sorted order. So before returning my answer, I just do a sort result dot begin result dot end. Now this is a SQL library in vector, which will help me sorting this vector. So I hope this works fine. Yeah, it works fine. And let's see, like when I have solved this problem earlier, 3 attempts, that means I have solved. So it was 2022, 2 years. And what did I make wrong here? Okay, I ran it to n minus 1. Actually, it has to be n. And here, since I was iterating my mask from 0, and I said we don't need an empty subsequence, so like I was doing this, right? If it was not, if size was greater than 0, so I am only convenient. But here we ran from 1 only because we know we don't need an empty subsequence. So this was a today's problem. Only thing was this line and this line. Why we're iterating till here? And so simple intuition I want to give you at the end also. Let's say if you have 1, 3, and you say this 1 sometimes can be 0 or can be 1. So you have two possibilities at every index. So it would be 2 raised to the power n. Same is in recursion. You have at every index you have a choice either to take it, either not to take it, either to take, either not to take. So at every index you have two possibilities. So overall you have 2 raised to your n possibilities, and that brings us our range. Why minus 1? Because when I gave 2 raised to the power 4 16, it would be 1 0 0 0 0. But since we are only concerned about these, so I'm checking for these. Let's make one it's one time. Let's make it 0. And we know till 16, this is the like we can see the beauty of the binary representation, that these the binary numbers will give me every configuration that I need. So I think this is clear. Again, why 1 lectured by n? I tried like I explained you this syntax uh, like most of the times in this video. Like if you want 1 left shift by n, that means we are shifting R1 by n bits. So we are moving. And when we do left shift, it is actually multiplying by 2. You can do the same thing using power 2 raised to the power n. And this one, we are looking is the ith bit is set in my mask. Mask is nothing but the binary representation of these. Here it is not dealing with binary representation, but when we wrote and here, actually it is checking for the binary representation. Let's say if my mask is 6110, so this mask actually feels like 6, but it is 110 because we have bitwise and here, and it is checking is ith bit is set in this mask. 0 bit is not set. 1th bit is set. That means I can include this one. This bit is set. That means I will include this one because this will return 1. If mask and 1 left by I means is my ith bit is set in my mask. You can see in this mask 1th and 2th bit are set. So the subsequence we will form from here would be AB. So this is the problem, and I hope this problem would be clear. Time complexity would be 2 raised to the power n cross n for this because there are 2 raised to the power n ways, and for every uh, every way we are iterating for n to check do we meet the desired configuration. This is 2 raised to the power n. This might not feel 2 raised to the power n, but actually this is. If I write this, this is actually 2 raised to the power n. So 2 raised to the power n ways we have. And for every configuration, like for every mask, you are checking what to take, what and not to take, and this is we are doing in order of n. So time complexity is 2 raised to the power cross n. And the space complexity is like answer it is an auxiliary space. So you can say an auxiliary space of order of n, sorry, order of 2 raised to the power n. Space complexity is also 2 raised to the power n because we have 2 raised to the power n subsequences. Also, in addition to this, we have also an order of 2 raised to the power n log n because we have 2 raised to the power n subsequences. So boiled down, if I had to write time complexity, let me mention here only. Time complexity would be an order of 2 raised to the power n plus an order of 2 raised to the power n log 2 raised to the power n. Why? We have, these are not n here, we have 2 raised to the power n subsequences. 2 raised to the power subsequences log 2 for sorting, and for this is like for iterating here. Actually, this is 2 raised to the power n cross n plus this is of sorting the vector, and space complexity is also actually order of 2 raised to the power n, but you can say this is an auxiliary space used for answer vector. So these are the time and space. Let me check for once that I didn't make anything wrong. 2 raised to the power n cross n plus for sorting because we have 2 raised to the power n elements in our result also. So log n. Space complexity would be this. Don't be confused by this. You know what is n log n. Here we don't have n. Here we have 2 raised to the power n subsequences. So that's why 2 raised to the power n log 2 raised to the power n. This is a space and time complexity. Only two things are there. This mask and this. How we are checking that is the particular bit is set in that mask or not. I think you get to uh, understand this algorithm. You can do a problem. I think there is problem subsets in lead code, which is actually the power set only. But after that, do that problem, and you will get a hand to an implementation again. So like let's say a repetitive practice. I think subset is the problem. Yes, subsets. So thank you, and not at this side.